Good afternoon everyone, and welcome to today's worked exam answer video. Today I'm having another look at a calculation based question, and this calculation comes from an AQA, I think it's an AS paper, but again equally it could be in an A-level paper. And the topic is energetics, and in particular we're having a look at a calculation for a calorimetry experiment. So when we're measuring the heat energy change and using the number of moles to then calculate the enthalpy change. I chose this question because it's not your straightforward Q equals MC delta T, get Q, use that to get delta H. Here we've been given delta H and we're going to have to work backwards because what we're trying to figure out is the final temperature. There is then a little one marker at the bottom thinking about percentage uncertainty, which I also want to address because this commonly comes up in relation to this experiment, but it also comes up in relation to other experiments as well. So I will have a look at that one too. So to get started, we're told that in a different reaction or a different experiment to the earlier part of this question, we have got 50 centimetres cubed of 0.5 mole per decimetre cubed aqueous hydrochloric acid being reacted with 50 centimetres cubed of a 0.5 mole per decimetre cubed aqueous sodium hydroxide solution. So first thing I'm going to do, as I always do with acids and alkalis in whatever form they are presented, is everything to do with my alkali in purple, everything I'm told about my acid in red. We are then given a balanced chemical equation for this reaction, which is going to be important because we can see that the acid and alkali react in a 1-to-1 ratio, which I can pop down. And then after the balanced chemical equation, we've been given the enthalpy change for this reaction. So delta H is minus 57.1 kilojoules per mole. Now, a couple of things that we're going to need to think about with regards to that value. The one that I'm going to mention straight away is the fact that it's negative. And any value for delta H that is negative tells us that the reaction in question is exothermic. So heat energy is being given off when sodium hydroxide is reacted with hydrochloric acid. I'll come back to that when we get onto the calculation in a minute. Then we're told that the initial temperature of each solution is 18.5 degrees, and we have to calculate the maximum final temperature of the reaction mixture. Then, as will always be the case, we are given the specific heat capacity. Now technically that's for water, which is why it says assume that the specific heat capacity of the reaction mixture is that. And again, we're given the densities of the reaction mixtures, and again we're using the density of water because it makes things a bit easier for us. So assume the density of the reaction mixture is 1 gram per centimetre cubed. Okay, so if we want a final temperature, we need to know what the change in temperature is. We need to know what delta T is. In order to know what delta T is, we need to know what M is, what C is, and if we then rearrange that equation, what Q is. We can't get Q from anything we've been told directly in the question. We're going to have to figure out what Q is. So there's two equations we're going to need here. Q equals MC delta T, and then Q divided by moles is equal to delta H. So if we were doing a bog standard forward kind of working question, you would probably be given M, or you could work out M from the question, you'd be given C, and then again you could probably work out delta T because you'd have a start temperature and a final temperature, get a value for Q, figure out the moles of whatever it is that you were using, whether it's neutralization or dissolving or displacement or combustion, and then using the value of Q and the moles we can figure out delta H. As I've already said, we've got delta H, so we're going to have to work backwards, and ultimately we want to get delta T. So delta T is going to be equal to Q divided by M and C. And as I said, we can get M from the question, C from the question, Q we can't. So then we're going to have to rearrange this equation as well. So we have Q equals delta H times by moles. So because we need Q for this second equation, we'll start with this equation on the right hand side here and address what each of these values are going to be. So delta H is minus 57.1 kilojoules per mole. We're not going to put the minus sign into our calculation though. And if we think about it again in a normal calculation, the value that you get on your calculator for these sorts of calorimetry calculations will always be positive. It is then up to you to decide whether, based on how the temperature is changed, whether the reaction is exothermic or endothermic. And if you think it's exothermic, because the temperature of the surroundings has increased, then you would manually make it negative. So that negative sign there, we would have manually put that in had we have been doing a calculation to figure that out. So therefore, I don't need to include it in working backwards to get Q and then delta T, because it was manually put in by us to show that the reaction was exothermic. So I'm just going to use 57.1 for my value of delta H, and then we need to times that by the moles. Now the moles of what? We've got the moles of sodium hydroxide, we've got the moles of hydrochloric acid. Now I said that they're in a 1-to-1 ratio and that I'd come back to that. That tells me that it doesn't matter whether I use the moles of the sodium hydroxide or the moles of the hydrochloric acid, because we've got the same volume of both of the solutions, we've got the same concentration of both of the solutions, so we've got the same moles of each and they react in a 1-to-1 ratio. Had we have not had the same volumes and the same concentrations, then we wouldn't have had necessarily the same moles. Then we would have had to have figured out which of these was in excess and which one was the limiting reagent. And if you have to do that, remember we always use the limiting reagent for any further calculations, because if a reagent is in excess, kind of by definition, it's not all going to react. So we can't therefore think, oh yes, when all of these moles have reacted, this is the amount of heat that was released. Can't do it like that. So neither of them are limiting because we've got the same volumes and the same concentrations. So I'm going to need to work out the moles from the concentrations and the volume. So moles is equal to concentration times volume. And what we also need to remember is that volumes should not be in centimetres cubed, they should be in decimeters cubed. So I'm going to times that by concentration, which is 0.5. And then that would be timesed by the volume, which is 50 centimetres cubed, divided by 1,000 to get it into decimeters cubed, which is 0.05. Obviously, I would not have done this here if I was doing an exam. Please do not write in this section. As it tells you here, it affects how it gets scanned in and whether you'll get the marks or not. So forgive me for doing that. I should have just started underneath. My bad. If I put that into my calculator, I get an answer of, for Q, 1.4275, and that's going to be in kilojoules. And I know that's going to be in kilojoules because delta H is in kilojoules per mole. We're timesing it by the moles. So that's going to be in kilojoules. However, again, if we think about how we would do this going forwards, once we've figured out Q, we would always then be changing Q from joules into kilojoules so that we got units of kilojoules per mole for delta H. So what I now need to do before I go on to this second equation is remember to times Q by 1,000. And if you don't, you're going to get a very, very, very small delta T, which hopefully would prompt you anyway to think about why and to go back and recognise that Q needs to be in joules. So that becomes 1,427.5 joules. Okay, now we're in a position, now that we've got Q and we've been given C, the specific heat capacity, 4.18, to figure out delta T, because M is the mass of the solutions that, or the solution rather, that experiences the temperature change. So in this experiment, 50 centimetres cubed of acid are reacted with 50 centimetres cubed of alkali. Many different ways we can do that, but fundamentally you are going to end up with 100 centimetres cubed in your beaker, polystyrene cup, however you're going to do that. All of those 100 centimetres cubed of solution are then going to experience the temperature change. So because the density of the reaction mixture is 1 gram for every centimetre cubed, if we have 100 centimetres cubed, we have 100 grams for our mass here. So with neutralisation, when we're adding the two solutions together, you have to remember to add the two volumes together because they'll both be in the same vessel. All of that solution will be experiencing the temperature change. So delta T, therefore, is going to be equal to the 1427.5 of Q divided by 100 grams for the mass, which we use the density for, and 4.18. And when I pop that into my calculator, I get an answer for delta T of 3.415. Now at this point, people might be noticing, the specific heat capacity has units of Kelvin to the -1, whereas the initial temperature is in degrees, 18.5, and therefore what actually is delta T in? Well, the change in temperature would be the same whether we were doing it in degrees Celsius or Kelvin, because if we had, say, 10 and 20 degrees, the difference would be 10 degrees. If we converted our 10 degrees into Kelvin by adding 273, so that would become 283, and 20 degrees, we added 273, that would become 293 Kelvin, 283 Kelvin, 293 Kelvin, the difference is still 10. So it doesn't matter whether your delta T, well, delta T won't really, I suppose it does have units, be it degrees or Kelvin, but it doesn't matter which they are, because for the change it will always be the same. So that is our change in temperature. Now we're on the home straight now. Now we can think about what the final temperature of this reaction mixture was. We know the initial temperature is 18.5, so something for the final temperature, take away 18.5, has to equal 3.415. Now, how did I know that I was taking away the initial temperature? Well, what we now need to do is think, is this reaction exothermic? Is this reaction endothermic? And again, comes back to that lovely negative sign there. That tells us that it's exothermic. And in an exothermic reaction, the temperature of the surroundings, which is what we're measuring, is going to increase because heat is going to be released to the surroundings. So it's going to be 18.5 degrees Celsius for our initial temperature, add delta T, so 3.415, and that's going to give me a final temperature of 21.915. And before I write that down, I'm just going to come back to the question and see how many significant figures we've got. It's looking like 3 for every value we've been given. So I need to give my answer to 3 significant figures, so 21.9 degrees C. Had the reaction have been endothermic, endothermic reactions take in heat, and therefore the final temperature would have been lower than the initial temperature. So we would have done 18.5 take away delta T to get the lowest temperature reached. I think it possibly also, I'm not sure whether that maximum final temperature is a bit of a clue. Maximum, we tend to think big, but I guess maximum could be it's getting, or the temperature is decreasing, but it's kind of like the maximum drop. So possibly useful, possibly not. this is going to be the key. If it's negative, exothermic reaction, temperature goes up, initial add delta T gives us the final temperature, or if it's positive, it's endothermic, temperature will go down, initial temperature minus delta T for your final temperature. Now that is a really, really small temperature change. You may have done this practical or a very similar practical. You may be about to if you're in year 12 and you've not yet started this topic yet. But one of the required practicals is combusting alcohols. And then there is another part of the required practical which tends to be something like this, where you've got two solutions being added together and we measure the temperature change over a period of time. You will have found that your temperature change was probably bigger than that, particularly for the combustion of alcohols. That will have been fairly substantial. But some of that is caused by the way in which they've set up this experiment, and that's kind of what they're getting at in 4.4. So we're being asked to suggest how, without changing the apparatus, the experiment in question 4.3 could be improved to reduce the percentage uncertainty in the temperature change. So I guess the first thing I need to make sure that we're happy with is, how do we calculate percentage uncertainty? What does that mean? The percentage uncertainty is based on the equipment that you use. That will give us the absolute error. So no piece of equipment is perfect. There are some pieces of equipment that are more precise than others, but each of them will come with a little error range. So for example, when we're using a thermometer, it might be that the temperature that we've measured is 20.0, but actually it could be maybe 19.9 or maybe 20.1, and that's not human fault, that is error on the equipment. And every piece of equipment has an error like that, whereby we might not exactly have measured what we think we should have measured. So that's one thing that affects percentage uncertainty. The other is the value that you are measuring. So with temperature, we would have the initial temperature, final temperature, and when we do temperature changes, we would then be looking at the errors on both individual readings, and they would come together to give us the overall percentage uncertainty in a temperature change. So if percentage uncertainty is worked out by doing the absolute error, which is from the apparatus, divided by the measured value, and we are measuring a very, very small temperature change, you're going to have quite a high percentage uncertainty. So if you've got a small number on the bottom here, you're going to get a bigger percentage uncertainty than if we had a bigger number on the bottom here. Now we're told we cannot change the apparatus. So the absolute error, which is coming from whichever piece of equipment we're using, that can't be changed, because that will only change if we change the piece of equipment that we're using. So with thermometers, we can use a standard lab thermometer, which kind of measures to every half a degree. But there are more precise thermometers where you can measure to every 0.1 of a degree. But we can't say that that's what we would do here, because we can't change the apparatus. The question has banned us from doing that. So if we can't change the absolute error, we have to change the measured value, and we need to make the measured value bigger. So how could we, therefore, get a bigger temperature change so that the percentage uncertainty decreases? And if we understand that that is what we need to think about initially, then we can go back to whatever practical it might be and think, right, that's what I need to achieve. What can I change with my experiment that will cause that to happen? So here, the measured value needs to increase. So we need to increase the change in temperature to decrease the percentage uncertainty. And you're not going to get a mark for saying that. I'm writing that there so that you can see my thought processes, and also so that you can refer back to this if you're attempting any other question of this ilk. There will be lots of them, like I say, and it won't always be about temperature change. It might be to do with mass change. It could be to do with measuring volumes with pipettes versus measuring cylinders, or it could be thinking about your mean titer used that you've worked out, from a titration when we're using a Biuret, and thinking about, again, how can we reduce the percentage uncertainty. Whatever it is that you're measuring the percentage uncertainty of, we're going to need to think about how we can increase the measured value if we're not allowed to change the apparatus, because increasing this is going to decrease the size of our percentage. So in this case, the only way that we can change the temperature change is, well, in my opinion, one of two things. We need to either change the volume of the two solutions that we're using and decrease the volume of the two solutions that we're using, because 100 centimetres cubed is quite a large volume of solution to try and warm up. So that's what the specific heat capacity is telling us. It takes 4.18 joules of energy to raise 1 gram of solution by 1 Kelvin. So if we've got 100 centimetres cubed of solution, we're going to need to have quite a lot of energy being put in to do that. If we were to decrease the overall volume, so maybe we could use 25 of each with half the volume, and then heating up that volume of solution would be easier, and thus we'd experience a greater temperature change because we'd get a greater final temperature. Or, in my opinion, the other thing we could do is increase the concentrations. So if we make them more concentrated, then we're going to get more of a reaction. We're going to increase the concentration by having more moles in the solution. Therefore, there's going to be more particles that can react, so therefore longer reaction, greater increase in temperature. And they're the only things that we can change here. We can't start really talking about equipment. Yes, if we were to make sure that we were doing it in a polystyrene cup that was stood in a beaker that had a lid on it, and we were thinking about stopping heat loss, that is still going to increase our temperature change ever so slightly. But again, that's coming back to changing the apparatus. We don't know what apparatus is being used, so we can't comment on that. So it'll always come back to thinking about the amounts of substances that you've got in the question. So to reduce the percentage uncertainty, we would need to decrease the volumes of the HCl and NaOH, or increase the concentrations of the HCl and the NaOH, and they would both have the same effect in that we'd get a higher final temperature, get a bigger temperature change, therefore decreasing our percentage uncertainty. Hopefully that's been useful. If you've got any questions about either part of the question, then obviously please get in touch with me. You can leave a comment on the video, or you can drop me an email to missgtutoringandresources@outlook.com. If you find other questions like this bottom one, the suggest one, with regards to reducing the percentage uncertainty, and you want me to work through other scenarios like that, so perhaps it is one where the mean titer is quite small, or maybe it's one where the change in mass is quite small, let me know, send it over to me, and I can definitely work through it. Hopefully that's been useful, guys, and I hope you have a lovely weekend ahead.